Welcome to our next lecture on AC circuit analysis. Our today's topic is AC power analysis, and this is based on the chapter number 11 from our textbook, which is Fundamentals of Electric Circuits by Alexander and Sadiku. I am Dr. Mohsin Shehzad. Power is the most important quantity in electric utilities, electronics, and communication system because such systems involve transmission of power from one point to another. So, in all these system electric utilities, whether you consider the electronics and communication systems, all these transfer power from one point to another point. So, power is very crucial quantity to be discussed. And we are always given the ratings of different appliances and devices in terms of power, and if we exceed the power rating we can permanently damage the appliance or devices. Therefore power is important and we must not exceed the provided power ratings. Instantaneous power, P of t with small p, is absorbed by an element is the product of its instantaneous voltage and the instantaneous current flowing through it. As given by equation number 1, P of t, the instantaneous power, small p, is given by the product of instantaneous voltage and current. And instantaneous power is always measured in watts, and the power at any instant of time. It is the power at any instant of time. We can also think of the instantaneous power as the power absorbed by the element at specific instant of time, and it is the rate at which the element absorbs some energy, as we know from our basic knowledge. Instantaneous quantities are denoted usually in lowercase. So, in case of sinusoids, for example, if we are given with some system where the voltage source is sinusoidal source, it provides terminal voltage, instantaneous voltage of V of t, and there is some passive linear network connected to it, and the current I of t is flowing into the passive network. So, instantaneous voltage is given by Vm cos of omega t plus theta v, and in phasor form we can write it as the amplitude and phase angle. Similarly, I of t is Im cos of omega t plus theta I, and in phasor terms it can be written as I and angle theta I. So when we multiply both these quantities we get the instantaneous power, and multiplying both these Vm Im cos omega t plus theta v times cos omega t plus theta I, and using this trigonometric identity, trigonometric conversion, we can simplify this P of t from equation 3 to P of 3t in equation number 5. And what we can see from this equation is that it is instantaneous power is composed of two components, one of which is a constant part, whereas the other is time dependent function, time dependent portion. So instantaneous part has two parts. First part is constant, time independent, and its value depends upon the phase difference between both the voltage and currents, like it's mentioned here, theta v and theta I. So greater the difference between these two, we will reach the smaller value and so on. And similarly, the other part is half Vm Im. This is constant amplitude of this sinusoid, which has double the frequency as compared to the frequency of voltage or current. As we can see from our previous slide that the frequency is omega for current and voltage. However, the frequency here for this power instantaneous part or time varying part of the instantaneous power is double. So, and there is a phase difference which equals the sum of theta v and theta I. So, when we plot this quantity, this is something a bit climbed up from zero level to the level of half Vm cos theta v minus theta I. This is the average value of the instantaneous power, and this is the sinusoid as represented by this blue part of the equation. So, as I mentioned earlier, the frequency is doubled for instantaneous power, and here is a bit small discussion about that. The time period is 2 pi by omega because 2 pi f is the omega and 1 upon f is time period. So, with this conversion, we can see that the time period for voltage or current is 2 pi by omega. However, and secondly, from this diagram, from this waveform, we can see that the P of t is also an instantaneous and time periodic function. It is varying at constant time period. Therefore, we can see that it's a periodic function. We can say that it's a periodic function, and P of t is equal to P of t plus t naught. Period of power is t naught is equal to t by 2, where t is the time period of the voltage or current, because the frequency is twice as the voltage, as we can see from equation 5 on our previous slide. So P of t is positive for some part of each cycle, means power is absorbed by the load, by the circuit, and negative for some part, which means that the power is delivered from the source to the load. For example, if we see this waveform, for this smaller portion, the instantaneous power is negative, which means that power is fed back from the load to the source. Whereas for this whole positive portion of the waveform, it means that the power is traveling from the source towards the load. Next, we are going to see the average power. Instantaneous power changes at every instant of time, therefore it is very difficult to measure. So what we do is we try to find out the average value of the power so that which is convenient to measure. Usually the watt meters respond to the average power. The average power P with capital but not bold in watts is the average of the instantaneous power over one period of time. So instantaneous power is given here for one time period. It's uh, when integrated over one cycle, it gives us the average value. Uh, it is important to see that we are using term capital T instead of T naught. Capital T was the time period for the current and voltage, whereas T naught was the time period for the power, instantaneous power. So if we want to take T naught here, we can take it because it's a periodic function and the average value of the power calculated for one cycle will remain similar for any number of cycles. So whatever the cycles are considered, if we consider whole cycle, then average value will not affect. So in this, with this argument, we can use T naught or T, either of them here. So by integrating, as we already saw, that this portion, this term, instantaneous power, consists of two parts. One is the constant part, whereas the other is the time dependent part. So this constant part comes out of integration, and we just integrate d of t from 0 to t, and this portion, this cos 2 omega t plus theta v plus theta I would be integrated. So for constant, average is same constant, so in this will remain similar, whereas for sinusoids the average value over the time is 0, hence it vanishes. This means that this portion, blue portion, will result to 0 because it's an integration of a sinusoid. whereas this term is an integration of a constant, so it will result in a same constant. Therefore, the average power would be this value. So when we plot it, we can get, when we plot it, we can, for average power, we get the same dotted line as we saw here. This is the average power of this system with instantaneous power of small p of t. So cos theta v minus theta I is equal to cos theta I minus theta v. So because cos of theta plus theta is equal to cos of minus theta always, therefore it's not important which one quantity we write first and which one second. However, the important point is that there we know about their phase angle in order to get the power factor angle. Secondly, P of t is time varying quantity, whereas the average power is not. To find the instantaneous power P of t, V of t, and I of t must be in time domain. The average power can be found if voltage and current are expressed in either the time domain or in frequency domain. It doesn't matter because it's a constant quantity. It does not contain any specific um, quantity which is time dependent. Therefore, it can be frequency domain or time domain, it doesn't matter. So, if we see like this, half of V phasor time I phasors conjugate, putting the values, what we get is half of Vm Im theta V minus theta I, and this is like this one. When we expand through the Euler's identity, we get cos of theta V minus theta I plus j times sine of theta V minus theta I. And this real part is, the real part of this equation number 9 is actually the average power. So we can write it, the average power is half of real part of this quantity. And why we are using this conjugate here, this is because of this negative sign. Because we need a negative sign here, so we used conjugate. And due to conjugate, as we already know, that the angle will be minus. So we can say that the average power is equal to half of the real part of the multiple of phasor voltage and conjugate of phasor current. Conjugate current is taken with respect to angle, as I have already mentioned. It's only because of mathematical reasons. Two special cases of equation number 10. What's equation number 10? This is equation number 10. And first special case is that theta v is equal to theta I. This means that current and voltage are in phase, which is only possible in case of purely resistive loads. So in that case, P is equal to half times Vm Im, because theta v minus theta I is equal to 0. So cos of 0 is unity. So we need not to write it here. And it is always equal to half times I square R, or half times phasor current I square R, where I square is I times I conjugate. And for purely resistive load, the load absorbs power for all the time. There are, from the waveform, for purely resistive load, the waveform would be like this. There will not be any portion, any part of the waveform below this zero line. So all the time the load is absorbing the power. Second point is Second case is when theta v minus theta I is something 90 degree plus minus 90 degree, so which means purely a reactive load, purely capacitive or purely inductive load. So in that case this angle would be 90 and this will result into 0, so average power would be 0. In this case our waveform would be like this one. So this sinusoid has equal portion above and below the 0 line, so it averages to 0. This is purely reactive load and absorbs no average power. A resistive load absorbs power all the time, while the reactive load, inductor or capacitor, does not absorb any average power. So now we look into an example of instantaneous and average power. We are given VFT is equal to 120 cos of 377t plus 45 degrees, and IFT is 10 cos of 377t minus 10 degrees amperes. Find the instantaneous power and average power absorbed by the passive linear network of figure 11.1. The instantaneous power is given by P is the multiple of V and I, and just multiply both these equations, and this identity we have already seen. We can put the values, so it's the constant part and it's the time dependent part. From here we can directly say that this is the average power. However, if we need to calculate it, we can calculate using this formula and it will result into same value 344.2 watts. Looking into another example, calculate the average power absorbed by an impedance Z is equal to 30 minus J70 when a voltage V is equal to 120 angle 0 is applied across it. So this is impedance, this is voltage in phasor form. So we need to calculate the average power absorbed by the impedance. So in order to get the current, just divide voltage by impedance, we get this amount of current. And to get the average power, just use this relationship, put different values, and by calculating, we get to the answer 37.24 watts. Similarly, another example, the circuit shown in figure 11.3, this one, find the average power supplied by the source and average power absorbed by the resistor. The current I is given by this one. So here we are given the voltage source, we are given the impedance, so which will be 4 minus J2, 4 minus J2 here. So in order to find the current, voltage divided by this impedance. So this is the resulting current in this circuit. So putting the values for average power, we get it's as 2.5 watt, and we also need the average power absorbed by the resistor. So this is the resistor, so we can find it. The current flowing through the resistor is same as this one because this is series current, and in order to find the power in the resistor we could use I square R or similar formula like this one. Voltage drop across this resistor 4 times I. So 4 is the value of resistance, IR is this value, so we get this voltage. Now that we have already the current and voltage values, we can just put and find the average power absorbed. And from this we can conclude that the total power absorbed across this capacitor is 0 because all the power delivered by the source is 2.5 watt, which is absorbed completely by the resistor. This means that this capacitor is not absorbing any power as we just saw in the previous slides. Determine the average power generated by each source and average power absorbed by each passive element in the circuit of figure 11.5. In this figure, we need to find the average power generated and by each source and average power absorbed by each passive element. So applying the mesh analysis, we can sorry we can find that the current in first mesh I1 is 4 because it's the same current flowing through here. And for I2, we write this mesh equation and find out that I2 is equal to 10.58 angle 79.1. So as we all know about both the currents, what we need to find is the power delivered power delivered by each of the source. So for the voltage source, current flowing from it is I2. For this voltage source is current I2 and its value is 60 angle 3. So the power by this voltage source is 207.8 watt. This is the same formula as we used earlier. This is voltage angle, this is current angle, this is voltage amplitude, and this is current amplitude. And this power is absorbed by the source in view of the direction and the polarity of the voltage. So the polarity is positive here, so it means that this is trying to push the current like this one. However, this current is I2 is flowing here, which means that this current I2 is forcing to flow into this battery, this voltage source. We can say that this voltage source is being charged with this current I2. And because we are having this positive symbol here, plus symbol here, this means that this current direction is correct. If this power would be negative, then we could say that this current direction is not correctly chosen. Actually, it is not charging this battery, but the battery is delivering power to the network. However, in this current scenario, the current I2 is flowing into the positive terminal of the battery, which means that it is delivering power to the voltage source. For the current source, the current through it is 4 ampere and the voltage across it can be found using this relationship. So the voltage across it is 184.98 angle 6.21, and using similar formula we can see that it's negative sign here, and we are using negative sign here because the polarity considered by us is opposite to that of the uh, flow of I1 current. So this means that this current source is actually energizing the rest of the circuit. This is supplying power to the rest of the circuit. Therefore, this negative sign is also indicative of this fact that current source is supplying power to the circuit. So, and for resistor, P2 is half of 80 multiplied by 4 because this is resistor, the voltage V2 across it could be found, and 4 is its value. The current flowing through it is 4, so voltage drop across it is 80 volt, and using this similar formula we can see that it's 160 watt. For the capacitor, the current through it is I2, which is 10.5 angle 79, and the voltage across it is minus J5 times I2, which will result into 52.9 angle minus 10.5. Sorry, minus 10.9. So when putting the values here, we can see that the average power absorbed by the capacitor is 0. Similarly, for inductor, we can see that the average power is also 0. So from this, we can see that the power supplied in this source is in this circuit is 367.8 watt from the current source, whereas the power absorbed by the resistor is 160 watt, and the current absorbed by the another voltage source is 207.8. Summing up these two, we must get this value, the supplied power, which we are actually getting. So this indicates that the power is conserved. There is no extra power. Power from all the appliances should be equal to 0. This is what is mentioned with this equation. With this, I close today's lecture and we will start our next lecture in our next video. Thank you very much. Goodbye.